Hello and welcome. These are your 5.2 notes. Okay, exponential model. So in 5.1, we talked about the basics of what an exponential function looks like. And today we are going to dive into it a little bit further and talk about how to apply this to financial situations and then how to build our own exponential equation. All right. Cool. So reminder from what we did in 5.1, we talked about exponential growth and exponential decay. The parent function for both is y equals a times b to the power of t. Now, t can be your input because it stands for time. You could also use x. They mean the same thing. The difference is that exponential growth occurs when our base is a number larger than 1. Exponential decay occurs when the base is smaller than 1. So I can actually substitute in this little equation for b, where for growth, b is 1 plus r. So this is really the same equation, just written in terms of r instead of in terms of b. And then for exponential decay, b is the same as 1 minus r, so that I could rewrite y equals ab to the t and replace the b with 1 minus r. So very similar. If we were to look at their graphs, just a note here, exponential growth means that as x approaches positive infinity, or as x goes to the right, y is going to shoot up, right? And then exponential decay is going to look the exact opposite way. So as x goes to the right, this is actually going to level off here. Okay. So then when we apply this to financial models or financial situations, we come across this thing called compound interest. My note here says when interest earns interest, this is called compound interest. Let's look at a very simple or simplified example. If I have $100 and I am going to earn 10% interest on that. All right. So if I have $100 and I earn 10% interest, 10% of 100 is $10. That gives me $110. Now, compound interest means that the next time I apply interest, instead of just taking interest on 100, the principal amount, the initial amount, I now get to take interest on the whole amount, 110, which is the principal plus the interest already earned. So if I take $110 and I add 10%, now I get $11 worth of interest. And this is how this grows exponentially, because now I have a larger sum. So when I take 10%, that number will be bigger, so on and so forth. Okay, so that's kind of how to describe compound interest. The compound interest formula is a little bit complicated. So I've got a is equal to p times parentheses 1 plus r over n, all to the power of n times t, where a is the final amount after however much time has passed. P is the principal amount, also called the initial amount. We use P because it starts with a P. R is the interest rate, always as a decimal. T is time in years. And N is a little bit new. It stands for the number of times interest is compounded in a year. So we're going to get into that a little bit more right here. I have this little statement. So if interest compounds blank times a year, then N is equal to so many. So that's what we're working with a little bit here. For example, if interest compounds annually, all right, annually means once a year. So then N represents the number of times a year. So if something's compounded annually, that means that N is equal to 1. If something is compounded semi-annually, so when I think of semi-annually, I think of a lot of stores have semi-annual sales, and that means twice a year. So semi-annual means 2 times, or you could think of semi, right, which means half. Quarterly, if you're a business owner, business owners often do their taxes quarterly, right? Civilians usually do it once a year, but quarterly would mean every 4 times a year. If interest compounds monthly, each month there are 12 months in a year. Weekly, there are 52 months in a year. And if interest were to compound daily, that'd be 365 times a year for most years, unless you're in a leap year like this year. Okay. Sam takes out a small personal loan of $5,000 at a 4% interest rate. Find the balance after 3 years for the chart. So what we're going to do here is we're going to look at when n is different values, all right, what happens to this amount. I've got the same initial startup amount of money, the same interest rate, the same amount of years, but the more times I compound, right, this is going to change. So we're going to go ahead and we're going to plug this in. Let's see. If it compounds annually, that means n is 1. So I plug that in my formula. A is equal to my initial amount, which is $5,000 times 1 plus, all right, so this is my principal, and 4% is going to be my rate, but I need to change 4% to a decimal, and that gives me 0.04. So this is 0.04 over n. N is the number of times it compounds a year, 1, to the power of n times t. So this is going to be 1 times t. In this case, t is 3 years. So I'm going to plug that in my calculator. When you're plugging this in your calculator, you've got to be a little bit careful here, because if you're not very careful with your parentheses and you try to plug this in, you could very easily make an error. So I suggest you plug things in one step at a time. So I would start on my innermost step, which is 0.04 divided by 1. I don't need to plug that in a calculator. That's just 0.04. And then I add 1. So I have 1.04 if I were to simplify this a little bit without plugging it in a calculator. And then I could raise that to the power of 3. So for me, if I were to do this in a calculator, I've got this little calculator app available. This is a free agreement with Texas Instrument, who is the same company that makes the calculators we use in class. They have allowed for anybody to download a 6-month subscription due to all of this quarantine and being out of school and having distance learning. So go to Texas Instrument and look for that free download if you do not have a TI type of calculator at home, a graphing calculator at home, and then you can use this while we were out of the classroom. So what you're seeing in this big screen here is what the little screen would look like, and then my steps are all going to be, the buttons I push are going to be on the left-hand side. So on my calculator, I would hit 1.04 to the power of 3, hit enter, and then I would take that and I would multiply that by 5,000. Now, a cool thing about this calculator is when I hit multiply, it automatically just assumes I want to multiply by my previous answer. So then I can hit 5,000 and enter. So I get this amount. So I've got $5,624.32. All right. If I compound semi annually, so all the information stays the same except for n changes to 2. So I plug this all in. All right, I just replace n with 2. And I'm going to go back to the calculator screen one more time. All right, so this time I'm going to plug in that fraction first, so 0.04 divided by 2. And I need to add 1 to that. And I need to raise that to the power. This time my power is 2 times 3, so I'm going to raise this to the power of 6. And then multiply by 5,000. If using this calculator is a little bit new to you, take your time and pause if you need to pause or rewatch that again. So I get this value, 5,630 and 0.812096, so on and so forth. I have to decide where I'm going to round here. The problem doesn't tell me where to round, but I'm dealing with money, so I'm automatically going to round to the nearest cent. So I look at 0.81, the next value is a 2, so it does not round up. So my answer here is going to be 5,630.81. All right. I'm going to go through the next 2 a little quicker. The beautiful thing about having this distance learning and having videos is that you can really work at your own pace. So take that, use that to your advantage. If you need to watch things multiple times, which I would imagine even myself as a learner, I would need to do that. Or if you need to pause it, take a break. If you need to pause it to do some figuring of your own, that is all extremely encouraged. So watching this one time through, I would not expect students to get the majority of this information. So really make this work for you and really use this distance learning to be self-paced learning. All right, so I've got these values. Now, a question at the bottom says, what do you notice from the chart in example 1? So as the number of times that this compounds a year, as the number of times I apply interest each year increases, what happens to my total amount here? Well, let's see, from annual to semi-annual, I make about $6, and as I go up here, I make a little bit more, and as I go here, I make a little bit more. So the change isn't vast, but it is changing. So as n increases, you can probably hear my dog barking, the final amount increases. Now we're going to write that, but this is actually going to be to a point, because eventually this is actually going to level off. If I were to, for example, if I were to plug in 1,000, if this, compounded 1,000 times, I would get I would get 5,637.47. So it goes up like $1.11. It's not that big of a deal to go from compounding monthly to 1,000 times a year. So it's gonna level off. And that kind of creates this interesting phenomenon where we can talk about something continuously compounding. So you've got two different formulas here. You've got this initial formula for compound interest, right? And then down here, we've got this new formula for what's called continuously compound interest. Because this is going to level out in a number, this creates an opportunity for us to discuss a new number called E. So this equation here is continuously compounded interest formula. A equals P times E to the power of RT. A is still the final amount, P is still the principal or the initial amount, R is the initial rate as a decimal, and T is time in years. This E number, this is not a variable, it does not change, it is a constant. It is a constant irrational number equal to 2.718281828, and actually that just keeps repeating. Think about your most famous constant irrational number, which is pi, 3.14159, so on and so forth. It's always a constant, right? It never changes. So E is kind of another type of number like that, a constant irrational. Let's go ahead and find it on our calculator because we're going to need it in our calculations. So I'm going to go ahead and I'm going to clear this. All right, and clear this. Perfect. All right. So to find the E button, I can't just use a letter. I've got to find the function of E, the number of E. And it is located where the LN is located. So on my physical calculator, this is capital L, capital N. On here, it's lowercase. It doesn't matter. This is the natural log button, which hopefully we'll get into maybe this year, maybe not. But written above it is E to the X. So if you can see where my tiny little cursor is here, I want to use this E to the X. So I'm going to hit my second and then E to the X. All right. Now it automatically prompts me with an exponent. And even if I don't want to plug in an exponent, I've got to put something in that box. So if I just do 1, right, anything to the power of 1 is itself, and then enter, then I get the number 2.718281828, and it just keeps going on like a pattern like that. The other cool thing about this screen is at the very bottom, you can see basically the steps that I hit to make this happen. So it could be helpful, especially if you pause it to recreate it. Okay, so let's see, we want to do e to the second power. So second ln, which gives me e to the power of, let's try 2, enter 7.389. And for practice, let's do e to the negative third. So second e to the power of. Remember that when I want to create a negative number in here, I have to use the negative symbol, which is down next to enter. You cannot use subtraction. If you try to plug this in and it gives you an error, chances are you used the subtraction symbol instead of the negative symbol. So be careful of that. Okay, make sure you're good. You know how to enter all of that. And we're gonna head back over to our notes. All right. So example 2, you invest $12,600 at a 3.2% interest rate, which is compounded continuously. So because it says compounded continuously, I know that I'm going to use A is equal to P times E to the RT. This looks like it should be a word. I call it A-pert. Doesn't make a whole lot of sense, but it's how it sticks in my mind so that I can remember the letters. How much do you have after 12 years? So if I invest this amount, this is going to be my principal value. I've got my interest rate here, so 3.2%. When I change that to a decimal, I move it over twice and I get 0.032. And then time is 12 years. So I'm looking for my final amount. My principal amount is 12,600 times E to the power of R times T, which is 12. So please go to your calculator and you want to punch this in. I highly suggest you punching in E to the power of first. So punch this in your calculator and then multiply by 12,600. Now you could also punch it in your calculator with just parentheses here and not have any issues. So punch that in my calculator. And we get 18,498.63. So if you didn't get that, stop this, go back, play with the calculator a little bit more, and figure out your order of operations for the calculator. All right, sweet. Now you try. So I want you to stop or pause this video, and I want you to give this question a try. Try to do it on your own. It says your best friend invests $125,000 in a fixer-upper house in Texas. Her mortgage has a 4.75% annual interest compounded continuously. What will she spend on the loan over the course of 30 years? Okay, you go ahead and compute that. And when you're done, come back. Okay, so when I plug this in, this is my principal value, 125,000 times E to the R, so 4.75. 0.0475 times T. And my time is 30 years. So if you look at this value, you could buy a house in California for $125,000. If it's a fixer-upper, if it's in an unpopular area, it would be very difficult to get a house for that amount of money. You could buy some land for that amount of money. So some other states have some cheaper counties and some other things available. This 4.75% is not a bad interest rate, especially for a first-time home buyer. So that's very realistic. And then most mortgages are a 30-year mortgage. You can get them shorter, you can get them longer, but traditionally that's what most people get into. So when we plug this in the calculator, you may find this number quite large. It's a little bit shocking. When I plug this in, you get 519,732.23, which means this person who got a loan initially for $125,000, if they make every single payment on time for 30 years, they will still end up paying more than $500,000 for this loan, which is why banks so very rarely go broke, because they make so much money on the money that they loan you. Now, if you can imagine taking this amount of money and maybe applying it to a typical house in Corona, which is probably about 3 to 4 times that amount of money. And imagine the amount of money you would spend in a loan over 30 years. It's a little bit intimidating, but good to know what you're getting into if you ever did make that step. All right. And the last problem set today, we are going to write an exponential model given 2 points. So what is an exponential model? This is just a fancy word for equation. All right. So we're going to write an equation given 2 points. And you've done this with different types of functions in the past. This one in particular is pretty similar series of steps as a linear function. But it's got some different things going on. So we want an exponential model. And an exponential model looks like y equals a times b to the power of x. We're not necessarily using time here, so I'm just going to use x as my input value. And if we go back to what we talked about last week in the 5.1 notes, we discussed how to identify an exponential function. And we're actually going to use these tools again in 5.3, so this is good. I'm going to write each one of these coordinates in a little mini table here. That's how we looked at it last section. And we talked that if when something is an exponential function, that it has a common ratio. So if I take the previous y term, I can multiply by some constant b to get the next y term. So this is a common ratio. And if you are a little unfamiliar with that, you could always go back and review the very beginning of 5.1 notes. So this creates an opportunity for me to make a little mini equation here. So I have 20 times b is equal to 26. And when I solve for b, I get b is equal to 1.3. So I know b already, and I've got this. But my equation is not complete until the only variables I have are x and y. So I need to continue to work so that I can find a. And this is how we'll do it. To find a, the only 2 variables are x and y. Ooh. So I am going to take a point from my given problem and plug in x and y. And it doesn't really matter which point you're going to pick. I'm going to go ahead and I'm going to pick 12 and 20. And when I plug that in, the y now becomes 20 to the power of x, which is 12. And I want to solve for a. When I go about solving this, if I were to punch 1.3 to the power of 12 in my calculator, I'm going to get some wild decimal. I don't want to risk rounding by doing 20 divided by that decimal. So I am just going to divide by the whole answer right here so that I don't lose any of my accuracy. So in the calculator, you could either do 20 divided by parentheses 1.3 to the power of 12, or you could do 1.3 to the power of 12, enter, and then 20 divided by that. If you want to recall an answer, I'll show you how to do it right here. All right. So if I want to recall an answer, for example, let's just do this one here. So let's say I've got 1.3 to the power of 12, and then I want to do 30 divided by that. So I would do, 20 divided by that. 20 divided by, now I want this answer. So above the negative sign is an answer button. On here, yeah, it looks almost the same on my physical calculator. Then you just hit second negative, which would give me an answer button, and I've got an error here because I've got 2 division signs. Let's try it all again. So 20 divided by the answer, and enter, and that gives me my answer. So when I divide, I get a is equal to about 0.858. The book does not clarify how many decimal places to round to here, so I chose 3. Hopefully that's consistent with what the homework asked for. I am not 100% sure. Hopefully I made that decision responsibly. So A is going to be 0.858 times 1.3 to the power of x. And then I have an exponential equation given points. This is approximate, right? I had to round for this A value. If you used the other 0.13 and 26, you should get something that is almost the exact same. The difference might be negligible. There might be a tiny difference, but it won't be significant if you do it correctly. Okay. I would like you to try to pause this video and try to do the second one on your own. If you're not comfortable with that, we're going to do one more together. So here we go. Same thing again. So I just wrote out what I want, and I've got my table here. I know that for an exponential function, this has a common ratio. So every y term, I'm going to multiply by a constant b. This creates an opportunity for me to write a little mini equation. 32 times b is equal to 40. And when I divide both sides by 32, I get b is equal to 1.25. Okay, so I know b now. And I need to plug in some point for xy. It doesn't matter which one you want to do. I'm going to do the second one this time, 8 and 40. I just like those numbers better. So I'm going to replace y with 40. And I'm going to replace x with 8. Now I can calculate this before I divide, but I am more likely to get an exact figure if I just keep it the way it is and not truncate this value. And then I plug that in my calculator. Oh, that's not very clear. Let me rewrite that. That is 1.25 to the power of 8. So I do 40 divided by parentheses 1.25 to the power of 8, and I get about 6.711. So I'm going to plug that in for A in for my final answer. And I have an exponential equation again. Okay, wonderful. All right, so these notes are to help you complete the assignment through Google Classroom for 5.2. And it shouldn't be too many problems. Hopefully you find them very reasonable. I will be on Zoom meetings Tuesday and Thursday again this week, so please come with your math questions. I'd love to help you out, and I hope everybody is doing well and staying safe. And yeah, maybe I'll see you guys on video chatting. Take care. Bye-bye.